So hello and welcome everybody. My name is Katharine Leney and I am a particle physicist working on the ATLAS experiment at CERN. Today we're going to explore the mysterious substance that permeates our universe, dark matter. Now you might think that scientists have a pretty good idea about what the universe is made of now, right? But actually that couldn't be further from the truth, and we only know what less than 5% of the universe is made of. The remaining 95% is made up of matter or energy that we don't know anything about. And as someone whose job it is to understand the universe, I always find that slightly embarrassing. But how do we know this? So we first got hints that something was not quite right with our understanding of the universe back in the 1930s. The astrophysicist Fritz Zwicky was observing the rotation of galaxies in the Coma cluster, which is a group of more than 1,000 galaxies about 300 million light-years away. He made various measurements of these galaxies, including the speed they were moving at, and by looking at how much light they emitted, he was able to estimate their mass. So this was all very well and good, except that what he found was that based on the speed that these galaxies were rotating, they should have a mass of about 400 times what he had estimated in order to have a strong enough gravitational pull to counteract the rotational forces and stop everything flying apart. Now this could be explained if there was some extra matter adding to the mass of these galaxies, but the idea was largely ignored for a long time. Until the 1970s, when the astronomer Vera Rubin made a different measurement that led her to the same conclusion. She was studying how stars move around our neighbouring galaxy, the Andromeda galaxy. She had predicted that stars near the sparsely populated edges of the galaxy would move more slowly than those at the denser centre of the galaxy, where they would feel a stronger gravitational pull. However, what she found was that there was in fact no difference in speeds between those at the edge of the galaxy and those in the centre, and she thought that this could only make sense if there was some invisible matter forming a sort of halo around the galaxy and contributing more mass. Since then, we've been able to make more and more precise astronomical measurements using tools like the Planck telescope to make maps of the universe. And the more we look, the more evidence we find that something really strange is going on, and that the matter that we know about only makes up a small percentage of the universe. Now, it might be possible that all of this could be explained by a flaw in our understanding of gravity, but most scientists think that there must be a new type of matter, or dark matter, that can account for this. And alongside the dark matter, we need to have dark energy, which is pushing against the gravitational force of all that extra matter and allowing the universe to continue to expand. And when we calculate what fraction each of these, so the visible matter, the dark matter, and the dark energy takes, we find that there's this 4.9% of the visible matter that we know about, 26.8% is dark matter, and the remaining 68.3% is dark energy. Now, you probably read on the programme that this talk will have something to do with cake, and at this point you're probably starting to wonder what baked goods can possibly have to do with all of this, but don't worry, the time has now come. So, in addition to being a particle physicist, I have a slightly unusual hobby. I like to bake, as I'm sure many of you do, but I bake in a very geeky way. And today I want to share with you my recipe for dark matter cake that is an anatomically correct model of the universe. So you should be able to download a PDF of the recipe from the same place as you found this video, and then you can make the cake yourself. So to make the cake, you'll need some standard cake ingredients like flour, eggs, and sugar. But what makes this cake like the universe and not just any other cake? Well, first of all, just like the universe, it's quite dark because there's lots of chocolate in it, so that's good. In your cake, you'll also put chunks of white chocolate that represent the visible matter in the universe. There are chunks of dark chocolate that represent the dark matter, and then the whole lot is bound together by something that you wouldn't normally expect to find in a cake, beetroot. So the beetroot here represents the dark energy of the universe holding the fabric of space-time together. And don't be tempted to leave it out, because without it, this cake won't work, just like our universe wouldn't work without dark energy. Now, all of these three ingredients are in the correct proportions when you make your cake. So when you eat the cake, you can think of eating your piece of cake as being like carrying out a survey of a small part of the universe. And you can think of the rest of the cake as being like the vacuum of empty space. Just like in real life, the dark energy is going to be almost impossible to detect, but while you eat it, and while your friends and family eat it, I want you to keep an eye out for visible matter and dark matter, and keep a tally of how much of each you find. And you might be surprised just how little visible matter there is in the universe. And if you check out my other video here, then you can watch a demonstration where I'll show you how to decorate your cake to look like the universe. It's really easy to get this effect, so don't be put off. And if you're on Twitter, you can let me know the results of your cake baking and cake eating experiments using the dark matter cake hashtag. So we know that dark matter must be there. And as a particle physicist, the next question I ask myself is, what fundamental forces does it interact with? If I have some ideas about how it might interact, it gives me some clues about where to start looking. Now, gravity is one of the fundamental forces, and probably the one that you are most familiar with. We know that dark matter interacts with gravity because we've seen its effects on the movements of stars and galaxies. Astronomers have shown that the fabric of the universe is distorted by the huge gravitational pull of large amounts of matter that we can't see, and that light from distant galaxies follows the curve of space instead of going in a straight line. These galaxies appear, when we observe them, as strange halos instead of point-like objects. And from looking at how much the light's path has changed direction, we can work out how much mass must have been there. And this is more evidence that dark matter exists and proof that it does feel the force of gravity. But what about the electric and magnetic forces that we know are actually different manifestations of the same electromagnetic force? The electromagnetic force is carried by photons, which are particles of light. So we know that dark matter doesn't feel the electromagnetic force, because if it did, then it would interact with these photons, these packets of light, and we will be able to see it, which means that it wouldn't be dark. The strong nuclear force is the force that's responsible for holding the atomic nucleus together. Now, we're pretty sure that dark matter doesn't interact this way, because otherwise we should be able to see its effects on cosmic rays, very high energy particles such as protons that are produced in supernova explosions. The fourth and final fundamental force is the so-called weak force, and this is responsible for nuclear decay. Now, as far as we know, the only way to produce particles is by either the electromagnetic, the strong, or the weak forces. So since we've ruled out the electromagnetic and strong forces, we're left with the weak force by the process of elimination. Now, of course, that doesn't mean there's not some new weird and wonderful mechanism going on that means we could produce dark matter particles some other way. But for the moment, this is our best guess. Now, if dark matter does interact via the weak force, then they would get the rather unfortunate label of being called WIMPs for short. But don't worry, we're not just being mean to dark matter by calling them WIMPs. WIMP actually stands for a weakly interacting massive particle. And if dark matter is a WIMP, then we might be able to find it at the LHC, where I work. The LHC is an enormous particle accelerator, the most powerful in the world. It's 27 kilometers, that's 17 miles long, and in a tunnel 100 meters underground. It's near Geneva in Switzerland and crosses the Swiss-French border multiple times. So we use it to accelerate protons to almost the speed of light and then smash them together inside cathedral-sized particle detectors that we use to examine the debris. One of these detectors is called ATLAS, and it's the experiment I work on when I'm not making physics cakes. The ATLAS detector is 46 meters long, 25 meters high, and weighs a whopping 7,000 tons. There are 3,000 people working on the ATLAS experiment, operating the detector and analysing all of the data that we collect with it. Now, some of those 3,000 people, like me, comb through the data searching for new particles, some of which might be able to explain the mystery of dark matter. Now, if dark matter particles can be created at the LHC, then they would pass through the detectors without leaving a signal, and we would only be able to tell that these ghostly particles were there by looking for strange events where we don't see enough particles to explain the interaction. I hope you've enjoyed this brief tour of the universe today, and I really hope you enjoy making and eating some dark matter cake at home. If you use Twitter, then let me know how you got on using the hashtag #darkmattercake, and if you want more physics and cakes in your life, then follow me on Physics Cakes. And hopefully we will be able to meet in person at WOMAD 2021.